Log on, tune in, find out. Another good idea from Cambridge.
I'm David Wallace. I'm Director of the Newton Institute. Really delighted to welcome you all to this workshop, which is in honour of John Thompson and the award to him with the tits of the Abel Prize. So well done to you, John. I'm going to spend just a moment or two, if I may, half a minute, expanding on comments which I wouldn't normally make, because John is also a fellow of my college, Churchill College. Yeah? Now, Churchill is a great place to be. We are terribly proud of it. It has a focus on science and engineering, including maths. And if you look back over the fellowship of the college in the almost 50 years since it was founded, including Winston Churchill, who is the person in whose honour it was founded, including his Nobel Prize for Literature, there have been more than 20 members of the college who've been awarded the Nobel Prize, and obviously we're rather proud of that. However, there is, of course, only one person in the college who's been awarded both the Fields Medal and the Abel Prize, and of course that's John. And it's easy to say that, and you could have guessed it anyway, because there are only, in fact, at this point, 3 people who have ever been awarded both of these prizes. Yeah. Another, well, I don't know, this is a little test for him, but I'm pretty certain I've got that. Of course, you can't believe everything that you read on the web, but this seems right. Another, of course, is Jean-Pierre Serre, who will be here tomorrow, making this a truly incredible meeting. And the third is Michael Attia, who was the founding director here. Yeah. So the associate, now unfortunately, I'm certain that Michael would have wanted to be here, but he unfortunately, I know for a fact, is in the States at the 85th birthday of Isidore Singer. So if it hadn't been for Izzy's 85th birthday, I'm sure we'd have had all 3 double prize winners here with us today, which would have been, for this meeting, would have been really remarkable. Anyway, really delighted, John, and warmest congratulations again to you. Coming to more prosaic matters, the usual stuff. If you have any questions of practical issues or anything at all, please don't hesitate to ask. The staff are here simply to make this a great meeting and to facilitate your work here. So please don't hesitate to ask them. On an even more prosaic matter, would you please switch off your mobile phones, because we are recording and it can interfere, as you probably are aware. I think finally from me, it's really just words of thanks, obviously to Gerhard Meinhof and to Sasha for organising the algebraic Lie theory program as a whole, and also to 2 of them, and to Jan for particularly for conceiving of and organising this meeting. So I hope that the program looks fantastic. I just wish I were expert enough to benefit from it. But since I'm not, I have an excuse to go away and do the administration, which keeps this place ticking over. And that's what I'm going to do. But I hope you have a great meeting, and I will, of course, see you all again at the dinner tomorrow night. And I look forward very much to that. Anyway, Jan, thank you very much, and over to you.
I'm very glad to welcome everyone here. It's very nice to see so many of you here. And it's clear we'll have some wonderful talks from some wonderful speakers. I'd like to add just one thing. We were hoping to have Jacques Tietz here as well, and invited him quite early on, but unfortunately he couldn't come, so he phoned and sent his best wishes, but couldn't be here. But maybe I shall organize a card to be sent to him. Well, this is probably the time then to hand over to Michael Aschbacher. I'm delighted to welcome Michael Aschbacher to be the first speaker. He is at California Institute of Technology, and is one of the leading players in the classification of simple groups and broad areas of algebra. And he's going to speak today about N groups, 3' groups, and fusion systems. Michael.
I have to work the microphone. Can you hear me now? So from the title of my talk, maybe you can sort of tell that it's about local finite group theory and also these things called fusion systems. So I guess the first area of mathematics I ever got into very deeply was local theory of finite groups, and ever since it's been my favorite area of mathematics. Of course, I'm sure most people here know that John Thomson's at least the modern father of, or the father of the modern theory of local theory of finite groups. So I owe him a debt of gratitude for all the hours of pleasure that I've got out of doing local group theory. But I guess on a more personal note, certainly he and his family have been kind to me and my family over the years. I think most particularly, almost the first time I ever came to Cambridge, I think was in 1976. I can remember that because that was the year my first daughter was born, and we came here for 3 months in the late spring, shortly after Kirsten was born, which wasn't so good for my wife, since I wasn't such a great help to her, but John and Diane and Kari were a bigger help than I was. For example, I think Kari was probably Kirsten's first babysitter. So anyway, I have many reasons to be happy to be here at this conference, celebrating his receipt of the Abel Prize. So let's see. Here's my title. So N groups and 3' groups are, of course, finite group theoretic objects related to local group theory. Later on, I'll get to these things called fusion systems. Presumably, few, if anybody out in the audience knows what they are. Throughout this talk, P will always be a prime. Usually G will be a finite group. Maybe I'll start slowly here. Remember that a P local subgroup of this finite group is just the normalizer of a non-trivial P subgroup of G. And of course, the local theory of finite groups studies finite groups from the point of view of these local subgroups. So maybe I'll go through a very fast-paced history of local group theory, just try to put some of the things I'll say later in some kind of context here. So I guess I think of Celo's theorem perhaps as the first theorem in local group theory. So all mathematicians know at least a little local group theory. And then maybe I think of work of Bernstein and Burnside and Frobenius around the turn of the century as being maybe sort of the next important contributions to local group theory. And maybe for a long period of time there was a period where there wasn't so much activity in the field. That started to change in the 50s, particularly in work of people like Brouwer, Philip Hall, Michio Suzuki. Work sort of revived the subject. Then around 1960, there's sort of a watershed here in the subject, beginning perhaps with Thomson's thesis establishing the Frobenius conjecture, and then perhaps more important, a few years later when his work with Feit proving that all groups of odd order are solvable. And then continuing on in the 60s, there are lots of activity in finite simple group theory, particularly in local group theory. Lots of new ideas introduced into the field, particularly by Thomson. So then, as the 60s went on, toward the end of the decade there, it actually started to be possible to think about perhaps being able to classify the finite simple groups. So I mentioned two sort of important events took place in the late 60s, early 70s. For example, Thomson's work on N groups that I'll talk a bit about more later on here. Think of that as a test case for trying to classify the finite simple groups, certainly a model for that classification. And I think perhaps in 1969, anyway, roughly around then, Gorenstein gave his talk at the University of Chicago where he speculated on a possible program to try to classify the finite simple groups. So then we move on to the 70s. That was certainly a time of great activity in finite simple group theory, and local group theory was the most important type of mathematics involved in that work. So that was when I entered the field in the early 70s, and lots of people of my age became finite group theorist because of all the activity that was going on at that time. So then, of course, that work in some sense culminated with the classification of the finite simple groups. Depending on when you think that happened, Ornstein, I think, announced it in 1981, although perhaps his announcement was a bit early. So that's my quick history of local group theory, but I want to talk just a bit more about two strands from local group theory that took place in the 60s and the 70s. The first one will be involve 3' groups and so-called S4 free groups, and then the second strand involves the N groups and so-called N2 groups. So we need some definitions here. So again, G continues to be a finite group. So I'll remind you that a 3' group is just a group whose order is relatively prime to 3. That's one type of group we want to talk about here. A section of a group G is some group of the form X mod Y, a factor group, or Y is a normal subgroup of some subgroup X of G. And then if you have some group H, or group G is said to be H-free if G has no section isomorphic to H. So remember, we want to look at S4 free groups. So for me, S4 means the symmetric group on 4 letters. So we're looking at groups that have no section isomorphic to the symmetric group of degree 4. So one other little definition we need here, if you got some tower of groups, U, subgroup of V, subgroup of G, then U is said to be strongly closed in V with respect to G here. If so this is supposed to be U conjugated by G. For each element U and U, each element G and G, if conjugate of U by G happens to be inside of V, then actually it should even be inside of U. So in that case, we say U is strongly closed in V with respect to G. So this is a statement about fusion of elements of V and G, how elements of V are conjugate in G, and these fusion systems that we'll talk about later on. Some means to sort of abstract this notion of fusion in finite groups. All right, so of course Thomson determined all the non-abelian simple 3' groups, and of course those groups are the Suzuki groups. I guess since we're part of a Lie theoretic meeting here, I should say twisted V2 of Q, the Suzuki groups. Now, remember, S4 free group's a group that has no section isomorphic to S4. So if 3 does not divide the group order, then certainly the group's S4 free. So you can maybe think of S4 free groups as a kind of a generalization of 3' groups. And George Glauberman determined the S4 free groups. His proof's a lot different from Thomson's, or what little I know of Thomson's proof. So what did Glauberman do? Well, let's look at a CLO2 group S of G here in some S4 free group. And what George did was show that each such group has a non-trivial abelian subgroup, 2 subgroup of S. There's an abelian subgroup of S which is strongly closed in S with respect to G in the sense as defined up here. So all the elements inside this abelian subgroup that are conjugate in G to an element of S are already living inside this abelian subgroup. And what was the importance of that? Well, there was a theorem of Goldschmidt, a student of Thomson's, which determined all the groups with a non-trivial strongly closed abelian 2 subgroup. So that was a slick way to determine what these groups look like. So how does that work? Well, since we're going to be talking about fusion later on, maybe we should know about this theorem of Alpern's fusion system, which is, at least for groups, kind of the strongest general result on fusion. And it says that fusion in S is controlled by certain local subgroups, the groups normalizer and G of P, as P ranges over these fully normalized centric subgroups of not G, but of S here. Control of fusion simply means you can decide when elements of S are fused just by looking within the normalizers of these groups P here. So what does it mean for P to be fully normalized? It means that the normalizer in S of P is a CELO group of the normalizer in G of P. P is centric if P contains all two elements in its centralizer. So Alperin says you just have to look at these particular local subgroups to decide how elements of S are fused. So then Glauberman, kind of the heart of his proof is something called the triple factorization theorem. It's proved for two constrained S4 free groups. What's it mean for a group to be two constrained? It means that, so O of G here is the largest normal subgroup of G of odd order. You look at the factor group G mod O of G, it should have a centric normal 2 subgroup. And back here, supposedly, we know what a centric subgroup looks like. So this particular class of groups, these constrained groups will continue to enter into the discussion here. And in such groups, Glauberman could prove this factorization theorem, and then together with Alperin's fusion theorem allowed him to show that there was this strongly closed abelian subgroup. So maybe just skip forward a bit chronologically. At some later point in time, I don't know, 80s or 90s, Bernd Stellmacher gave a somewhat different proof than Glauberman's. He proved something stronger. He showed that if you have any 2 group S, then there exists some non-trivial characteristic subgroup of S, which is normal in any constrained S4 free group G. And then some more elementary results on fusion due to Glauberman together with Stellmacher's theorem are enough again to show that there's a strongly closed abelian subgroup. So anyway, there's kind of a progression here. Thompson's work on 3' groups, which is a little bit different flavor than the work of Glauberman and Stellmacher, which is a bit more fusion theoretic. So we'll come back to this strand of local group theory later on. So the second strand studies these N groups and N2 groups. So I remind you that a N group is a non-abelian finite simple group with the property that all its local subgroups are solvable. So, obvious test case for trying to classify non-abelian finite simple groups. And then a slightly more general class of groups. N2 groups are the let's just say now finite group, not necessarily finite simple groups, finite groups with the property that all now 2 local subgroups are solvable. So now we're only imposing restrictions on the 2 locals rather than on all local subgroups. All right, so and one more definition that's useful here. A finite group is a characteristic 2 type if every 2 local subgroup, let's say H of G, has the property, well, its generalized fitting group is equal to O2 of H. O2 of H is the largest normal 2 subgroup, but probably many of you don't know what that means. It means that H has no non-trivial subgroup, normal subgroup of odd order, and it's constrained. What this generalized fitting group is doing is keeping track somehow of the small normal subgroups of G. So what this is saying here is that all the small normal subgroups, whatever that means, are 2 subgroups. And just to motivate this definition, which we'll return to several times, if you know anything about the classification of finite simple groups, then you realize that the classification is partitioned into 2 halves, and one of the halves of the partition is to determine the simple groups of characteristic 2 type. So this is an important class of groups. All right, so Thompson, of course, determined all the N groups in a lengthy series of papers. I don't know, 400 or 500 pages in this series of papers, but more important than that is the fact that this N group paper in the first place, as I said, serves as a model for the classification, but in addition introduces lots of new ideas into local group theory. I'll give you just 2 examples here. Gorenstein was led to his theory of signalizer functors, whatever that is, and anyway, it's an important part of local group theory by studying the odd order paper and the N group paper. Second place, there's a notion of something called a strongly embedded subgroup in finite simple group theory, and I think it's probably true that this notion was introduced in the N group paper. In any event, it's the first place that I see this notion arising. So I'll recall for you that Helmut Bender showed that he determined all the groups with one of these strongly embedded subgroups. And the answer is that essentially a group with a strongly embedded subgroup is a group of Lie type of B rank 1 over a field of even order. There's some others, but somehow this is the interesting class of examples. So a modern way to look at the N-group paper, after Gorenstein and various other people, Goldschmidt and Glauberman, developed this theory of signalizer functors, and after Bender proves his theorem, one way to look at N-groups is the following. If you use signalizer functor theory, you use Bender's theorem on strongly embedded subgroups, then there's a fairly nice proof that if you have a N2 group, not just an N group, but an N2 group, then such a group is either of 2 rank 2. 2 rank is just sort of the largest width of some direct product of a bunch of groups of order 2. So somehow the 2 locally, this is a small group, or else the group is of characteristic 2 type. So here's some sort of dichotomy in studying N groups. You have these groups of small 2 rank or groups of characteristic 2 type. In the general classification, you have the same dichotomy, except groups of 2 rank 2 are replaced by a much larger class of groups. All right, so Thompson determined the N groups, and then later, building on his work, Janko, Fred Smith, Gorenstein, and Lyons extended this work on N groups to a determination of all simple N2 groups. And even later than that, again, probably in the 90s, again, Bernd-Stellmacher revisited this subject, and he did the following. So he looked at N groups of characteristic 2 type, which from this discussion is a reasonable thing to do. Different sort of mathematics is involved in that branch of the analysis. And so what did he do? He say, let's look at a CeLO2 group S of G, and let's assume that it's contained in more than one maximal 2 local, maximal with respect to inclusion in the group. And let's assume that the subgroup generated by this pair of 2 locals has no non-trivial normal 2 subgroup. Then this pair of groups gives rise to something that these days is known as an amalgam. So you encode the information that you get by looking at the inclusion maps from the intersection of G1 and G2 into the groups G1 and G2. So that gives you some sort of group theoretic data here. And essentially what Stellmacher did was to show that not exactly determine these amalgams, but get a lot of information about the possible amalgams here inside an N group in this situation. So later on we'll see that this is sort of approach that one can take more generally. So this is maybe one of the more modern ways to revisit this subject. So Stellmacher's approach involves something called the amalgam method. It's a tool for studying these groups of characteristic 2 type. It was developed by Goldschmidt, Meyer-Frankenfeld, Stellmacher, Stroth. And this mathematics is a little bit different than the mathematics that appears even in the portion of the N group paper that looks at groups of characteristic 2 type. In that portion of the paper, Thompson does things that I think of as weak closure methods. He did a precursor to this work of these guys here actually goes back to work of Tutt on trivalent graphs, and then some later work of Charlie Sims, and John did use Sims's theorem in his work on N groups. So he did use sort of a primitive version of this theory. All right, so that's enough on local groups, at least for a while. Let's talk a bit about fusion systems, which I assume most people have never heard of here. So notion of a fusion system and a saturated fusion system is due to Louise Pooch. I think probably work beginning in the early 90s. There's a caveat, however. A fusion system comes equipped with a P group, let's say S, and Pooch wouldn't call a fusion system on S a fusion system. He'd call a divisible S category, and he'd call a saturated fusion system a Frobenius category. So why is that? Why is he using different language than I am? Well, it's because he didn't publish his work until quite recently, and in the interim, homotopy theorists became interested in his work, found his work useful, and they introduced their own language. They introduced this language of fusion system saturation, and so that at this point in time, that's the language that's sort of become, the terminology that's become accepted. For example, I learned whatever I know about fusion systems from reading the work of homotopy theorists, and by now I'm tied into that language. So that's the language that I'll be using rather than Puch's terminology. So I should say that Puch developed these notions for purposes of modular representation theory. So you can see already that there are connections of these things with modular representation theory and homotopy theory, but I don't have time to go into that. I'm just going to concentrate on the relationship between these fusion systems and local group theory. So what is a fusion system? So we have our prime. Let's let S be a finite P group. You can look at these notions in more generality, but let's stick to this special case here. So a fusion system on S is a category, let's say script F. The objects of this category are the subgroups of S. I'll write FPQ for the morphisms in this category from P to Q, a pair of subgroups P and Q of S. And this set of morphisms should be a set of injective group homomorphisms from P into Q, and these axioms should be satisfied. There's various ways to say it. Here's one way. So again, this is P conjugated by S. For each little s in S, P conjugated. If P conjugated by S is in Q, then the conjugation map, the induced homomorphism from P into Q via the conjugation by S should be one of our F maps here in this category. And second axiom here, if we have some F map from P to Q, then also the map that we get by thinking of this map as an isomorphism from P to its image, that should also be an F map, as should be the inverse of this isomorphism. Okay, so that's what a fusion system is. We've got our P group, and we've got a bunch of injective group homomorphisms amongst the various subgroups of S, and there's enough of these guys around. So here's the standard example that you want to think of. Let G be a finite group. Let S be a CLO P group of G. Right, F sub S of G for the following fusion system. The fusion system F with the property that the F maps from P to Q are those that are induced by conjugation in G. So this is just keeping track of the fusion in S induced in G. That is when two elements in S are conjugate in G. And then what we're really interested here are these saturated fusion systems, and I'm not going to define that. It's a bit more technical. I'll just say that a fusion system is saturated if it satisfies two more axioms, and those axioms in this particular example are easy to prove just using Celos theorem. So these are axioms that were defined by Puch a long time ago. So finally, here's kind of the theme of the talk. What I'm going to do is try to convince you that some theorems on finite groups are best proved as follows. Take your favorite theorem on finite groups, try to restate it in the language of fusion theorems, prove the new theorem for fusion theorems, and then use the theorem about fusion systems to give a proof in the category of groups. So what I contend is that there are many theorems, particularly in local finite group theory, which are perhaps best proved using this approach here. And later on, I'll give you 4 examples of theorems about fusion systems, and then corollaries for groups. 2 of these theorems, at least as far as I know, are new theorems about groups, and 2 are theorems that we've been talking about. Okay, so let's see. We need some terminology, some notation, some concepts. So pretty much from now on, let's let F be a saturated fusion system on some P group S. We have some subgroup P of S. I'll use this notation P superscript F for the set of images of P under the various F maps of P into S. So these are the F conjugates of P. In our standard example, they would be the G conjugates of P contained in S. So we say this guy is fully normalized or centric if for every F conjugate Q of P, well, to be fully normalized, the order of the normalizer in S of P should be greater than or equal to the order of the normalizer in S of Q for each of these conjugates. To be centric, the centralizer in S of Q should be contained in Q for every F conjugate. And let's write F superscript little f for the set of non-trivial fully normalized subgroups of S. So what do these two notions correspond to in our standard example? Well, if you think a bit, you'll see that P is fully normalized precisely when the normalizer in S of P is a CALTECH group of the normalizer in G of P, and that P is centric precisely when it contains the centralizer in G of P. All P elements in the centralizer in G of P are already contained inside of P. All right, so here's some set of notions that we're going to need throughout the rest of the talk. All right, so we want to do something like local group theory in the category of fusion systems. So we need local subsystems of a saturated fusion system. So here's the right notion, and again, due to Pooch. So if we have some subgroup P of S, let's script N be the normalizer in F of P. What is that? Well, it's the fusion system on the normalizer in S of P. And then I have to tell you what the N maps are from subgroups, from a subgroup Q to a subgroup R of this normalizer in S of P. Well, the map phi, such a map phi is an F map with a property that extends to another F map, let's say phi hat, now from the group PQ to the group PR. Since Q and R normalize P, those are subgroups of S. Not only extending to such a map, but the extension should have the property that it acts on the subgroup P. All right? So this seems to be the right definition of the normalizer in F of P. Here's a theorem due to Pooch. If you have a fully normalized subgroup, then its normalizer is a saturated fusion system. Pretty easy to see that it's a fusion system. The saturation is harder. So in all these things, we've got our fusion systems, and then we have the smaller category of saturated fusion systems. Fusion systems behave very nicely. The saturation property doesn't always behave so nicely, but it's, can't do much without this saturation property. All right, so as I say here, these normalizers of these fully normalized subgroups P kind of play the role of the local subgroups in the category of fusion systems. An example, whoops, skipped ahead. All right, so here's two more notions here. So our subgroup P of S is normal in this fusion system, so somehow this should correspond to a normal subgroup in a group. It's normal in the fusion system if F is the normalizer in F of P, just as you'd expect. On the other hand, the system is constrained if it has a normal centric subgroup. Probably don't remember what a centric subgroup is. I should be using more. I have two slide projectors here I could be using. So there's the definition of centric. All right, so that's what normal means, and what constrained means. And here's an example. If we look at one of our standard examples, then the group G is constrained in the sense that I defined earlier. If you remember what it is, then you do, and if you know what you know. Then the fusion system is constrained, but the converse is false. And this is starting to get at why maybe it's easier to work in fusion systems than it is in groups. We'll have lots of examples where there's some notion of, for groups, when you translate into this category of fusion systems, that it translates, but somehow it's kind of nicer for fusion systems than for groups. So here's some important result in this subject due to 5 homotopy theorists. If our saturated fusion system is constrained, then there exists a finite group G such that the group S on which the fusion system defined is a CALTECH group of G, and the generalized fitting group of G is OP of G, is a P group, so all small normal subgroups are P groups. And F is the standard example associated to G. So this particular constrained fusion system does come from a group. Moreover, this group is unique up to an isomorphism, which is the identity map on S. It's essentially unique. So I'll call a group like this for a constrained system a model for the system. And the fact that these models exist sort of tells you that it's going to be possible to take arguments that you could carry on in the category of groups and at least in some cases translate them into arguments about fusion systems. I say it differently here. All right, so there's this notion of an exotic fusion system. It's a saturated fusion system which is cannot be realized as one of these standard examples. It's not of the form S sub S of G for any finite group G, for which S is a CLP group of G. And such things exist. There's some very interesting ones that exist. So again, if I was given a real talk about fusion systems, I should talk about them, but I don't really have time to do that, unfortunately. But anyway, I think of these exotic guys as somehow akin to sporadic groups in finite group theory. Okay, so let's see here. Let's look at some examples to sort of get some sense of the relationship between fusion systems and groups. So in all these examples, F will be the standard example for some particular group G and a CELA group S of G. So O sub P prime of G is the largest normal subgroup of G of order relatively prime to P. So let's look at the factor group that you get. Let's call it G star, and let's let star denote the natural homomorphism from G onto this factor group here, natural surjection. Then it turns out it's easy to see that the fusion system F for G, this guy here, is isomorphic to the fusion system, the standard example for G star. So the way I would say that is that these fusion systems somehow don't see these normal P prime subgroups. That information sort of disappears. And that could be good or bad. It could be bad because you're losing the information, or I prefer to look at it that it's good because somehow that complication is not entering into the picture. In particular, if you have a P local subgroup H of some group G, then probably it's Gorenstein who introduced the terminology that the core of H is the group OP prime of H, largest normal P prime subgroup of H. And it's a fact that in doing local group theory that these cores cause lots and lots of problems. For example, signalizer functor theory was introduced to try to help overcome some of the problems that the existence of these cores leads to. But you see here in the category of fusion systems, because of these examples, you don't even know that those cores are around. So all the difficulties in local group theory that they cause don't disappear here in this, if you try to do something analogous for fusion systems. Two more examples that show similar sorts of things. Suppose this CELA group S is abelian. Then again, it's easy to see that this guy up here is the same as the normalizer in F of S. And this fusion system is kind of a P-closed fusion system. It has a normal, this S is normal in that system. Why is that? That's just Bernstein's fusion theorem. It says that if you have an abelian CELA group, the normalizer of the CELA group controls fusion in the CELA group. So, you know, if you take your favorite finite simple group, take a prime divisor at random, almost always the CELA group is going to be abelian. So somehow, depending on how you look at it, things are easier or harder, and I think of it perhaps as being easier. So for all the various primes, divisors of a group for which you have an abelian CELA group, somehow things are very easy. Similar example, suppose you have a group G of Lie type of Lie rank 1 over a field of characteristic P for our particular prime P. Let's look at the normalizer in G of S, call that B. Of course, that's a Borel subgroup of G. And in this case, the fusion system for G is the same as the fusion system for this Borel subgroup. So again, S is a normal subgroup, not of G, but of the fusion system, of course. I mean, that's the point. It's normal in the fusion system, but not in the group. And why is that? That's because this unipotent radical, this guy S, is a so-called TI subgroup of G. If you take distinct conjugates of S in G, they intersect in the identity. So it's a triviality that fusion is controlled in this normalizer in this Borel subgroup. So again, somehow these groups of Lie type of Lie rank 1, fusion theoretically, they're almost not interesting. They don't cause you any difficulties, whereas in finite group theory they do. They're the examples that come up in Bender's theorem, for example. A final example, which perhaps shows you the limitations of this approach. So suppose we have two non-abelian simple groups, G and H. Let's take our prime P to be 2, and suppose S is a CeLO group of G, T is a CeLO group of H, CeLO2 group, and suppose these groups are both dihedral. Then it turns out it's easy to see that the fusion systems at the prime 2 for these two groups are isomorphic precisely when these dihedral groups are of the same order, when the dihedral groups are isomorphic. Okay? So what does this? This tells me that on the one hand, the study of two fusion systems on dihedral groups is kind of trivial. Just write down what they look like. Here's maybe the most interesting case where they come from simple groups. They all come from groups. But on the other hand, it also shows the limitations of trying to use fusion systems to study groups, because you know, when you do this fusion analysis here, you've done something. You know, elementary transfer and fusion tells you something about the group, but you know, you're a fraction of a way toward seeing what simple groups with dihedral CeLO2 groups look like. So I don't know, to the extent that I have intuition about this stuff, it seems to me that if the p-local structure of some group is sufficiently rich, then the fusion system tells you a lot about the group, and trying to translate group theoretic statements into the fusion category is a good one, whereas in the case of these dihedral groups, if the p-local structure is not rich, then you're not going to get very much by doing that. All right. So let's see. So from now on, let's let F be a saturated fusion system on some p group S, and pretty quickly I'll specialize the case where p is 2. So let's see. Remember we had groups of characteristic 2 type. Let's try to generalize that into the category of fusion systems. So let's define F to be of characteristic p type if for each fully normalized subgroup p of F, the normalizer in F of p is constrained. Okay? So remember G was of characteristic p type if for each a non-trivial p subgroup, the normalizer in G of p was constrained in a suitable sense. Okay? So this is the obvious generalization. Example, as I say, if G is of characteristic 2 type and S is the CeLO2 group of G, then the standard example at the prime 2 is of characteristic 2 type. But as we'll see pretty quickly, the converse is not true. Let's see, one more piece of notation we'll need here. Suppose we have some family of subcategories of this saturated fusion system. So let's define pointy brackets this family here. Think of this, if it was a group, it'd be the subgroup generated by this set of subgroups. Here's the subfusion system generated by this collection, this family of subcategories of F. So it's the, well, I'll say the subsystem of F generated by this family. What is that? It's just the intersection of all the fusion systems containing this family, and that will be a fusion system, although in general not a saturated fusion system. Okay. And really what Alpern's fusion theorem says is that for a fusion system of a group, that fusion system is generated by certain subcategories. All right, so now I'm going to, remember I said it's going to state four theorems about fusion systems and then derive some 4 corollaries. Actually, I won't bother in one case. Derive some corollaries about groups. So in these theorems, the prime p will always be equal to 2. So now we have a saturated fusion system, 2 fusion system. And let's say this guy is an obstruction to pushing up at the prime 2. If it's a standard example for some finite group G, where S is of course CeLO2 group of G, and it's one of these guys here, and you don't really need to look too closely at this list. If you know some local group theory, then you see there's a bunch of relatively small groups here, and if you know anything about working with groups of characteristic 2 type, there's this stuff called pushing up, and you know that somehow these groups somehow cause difficulties when you try to do this pushing up stuff. Okay, so somehow this is trying to translate some stuff that you do about groups of characteristic 2 type into category of fusion systems. So anyway, you've got some relatively short list of fairly nice fusion systems here, and we're going to call these guys obstructions to pushing up at the prime 2. I don't know. We'll leave this list. Okay, so here's the theorem. So suppose F is a saturated fusion system of a finite true group S. It's a characteristic 2 type. All these normalizers are constrained. If we look at the group of F automorphisms of any subgroup P of S, it's a K group. What does that mean? It just means that the simple sections in this group are on the list of groups that you're given by the classification. So if you believe the classification, this is not a hypothesis. But the point is that maybe I'd like to use some of these theorems to give some sort of new proof of parts of the classification of finite simple groups. So if you did that, you'd be working somehow in a minimal counterexample where you'd have this hypothesis. So that's why that hypothesis is there. So basically, it's a saturated fusion system of characteristic 2 type. So then let's look at the set script U of non-trivial normal subgroups U of S with some extra properties. The important property here is that these guys are normal in S. And then the statement is that F is generated by the normalizers in F of these non-trivial normal subgroups of S with extra constraints, sort of like in Alperin's fusion theorem. Oh, either that's true or else F is one of these guys over there on this slide, this relatively small list of fusion systems which will not satisfy this theorem. You know, they're actually counterexamples. Okay. So here's the corollary for groups. So now let's assume G is a finite group of characteristic 2 type in which all 2 local subgroups are K groups. You know, that's a translation of the hypothesis. Take a CL2 group S of G, then one of the following holds. So the analog of statement 1 here is that the groups, the local subgroups normalizer in G of U, as U varies over the normal subgroups of S with the property that the centralizer of S of U is contained in U, and U is the largest normal 2 subgroup in its normalizer. That set of subgroups controls fusion in S. Important thing here is that fusion is controlled by subgroups normal in S here. Or there's going to be some cases where that theorem fails. There'll be, as you see, some subset somehow of the groups that appear over there. And why is it? It's actually kind of a small subset. And why is that? That's because most of those guys over there, the groups that are appearing on that slide are not groups of characteristic 2 type. The fusion systems are of characteristic 2 type, but the groups are not. So I've extracted some sublist here from that list over here. Okay, so they're relatively small collection of counterexamples. So I'm going at a pretty good clip here, so maybe I can tell a little story here. So why did I prove this theorem? So in theory, Steve Smith, Ron Solomon, Richard Lyons, and I are supposed to be writing some book that's supposed to give an outline of the classification of simple groups of characteristic 2 type. Actually, Steve Smith and Ron Solomon are doing all the work. So Steve Smith reads along in some paper I wrote. It's on something called the uniqueness theorem, and somewhere near the end of the paper there's an appeal to a result of Pat McBride. And it's not clear what this result is because I don't even remember what it is, and certainly nobody else remembers what it is. But this would suffice. This theorem would suffice for that appeal. So Pat McBride, maybe after his postdoc or something, dropped out of mathematics and was working in some aerospace company, and turns out in Santa Monica. So Steve hunts him down and he says, okay, what's this theorem? So Pat McBride says, I've never proved any theorem like that. Doesn't remember. I even had a title for it. I have the vaguest idea where this thing came from. So anyway, that's why I came to prove this theorem here. Okay, so as far as I know, this is a new theorem about finite groups. Okay, here's a related theorem, a stronger theorem. So there's this thing called the Thompson group, J of S. It's a subgroup of S generated by all elementary abelian subgroups of S of maximal order. Thomson's original proof of the Fabini's conjecture didn't use this thing, but later on he got a nice slick proof of it, which uses the Thompson subgroup. And then later on, this guy Bernd Baumann defined this other subgroup, this Baumann group, that's a bit more complicated. Maybe we don't need to look at it too closely. maybe we don't actually need to look at the statement of this theorem too closely. So what does this theorem say? Roughly speaking, the same hypothesis as the previous theorem. Conclusion, well, either you get your same set of examples, these obstructions, and then there's another class, slightly bigger examples coming up here, or else again the fusion system is generated now not by the normalizers of all the various normal subgroups of S, but just, well, by the centralizer of one subgroup and the normalizer of another. So we've got two subgroups, C1 and C2. They're not quite characteristic subgroups, but they're F characteristic, whatever that means. So in particular, they're stronger than being normal subgroups of S. So in the first case, C1 is essentially the center of S, and C2 is this Bauman subgroup. So this fusion system is generated by essentially the normalizers of two characteristic subgroups, C1 and C2. So this is a kind of thing you want to prove for always for finite groups. So unfortunately, this is just for in the case of characteristic 2 type. So remember, Glauberman had this triple factorization theorem. What he really would have liked is a factorization theorem. So this is sort of getting at something like a factorization theorem, except it's a generation theorem for fusion systems. And here's one reason that you might like to have such a thing. There's lots of reasons, but here's one reason. So since these guys are constrained, these fusion systems here, let's say these two guys here, are constrained. So they have these models. So let's say G1 and G2 are models for the centralizer in F of C1 and the normalizer in F of C2. So the fusion system is generated by the fusion systems of these two models. So now, if you think about it a while, that says that this fusion system is determined by the corresponding amalgam. You remember these amalgams came up at some earlier point in time. G1 G2 intersect G2 isn't really right here, but somehow there's some analog of G1 intersect G2 here. So we have some sort of amalgam like this, some little group and inclusions of this little group into two big groups. And this amalgam is keeping track of this fusion system. For example, if you form the free amalgamated product of these two groups over this group here, you'll get some infinite group in which this guy S is somehow a CELO group. It has properties analogous to a CELO group in a finite group. And if you do your standard example in this infinite group, make the same construction, you get a fusion system, and that fusion system is the fusion system generated by these two subsystems. So that's one way to see that just the data embedded in this amalgam here is telling you exactly what this fusion system looks like. So for example, you might say, I'm going to go along here and try to classify fusion systems according to some properties. So somewhere at the end, I'm going to have to spit out a fusion system. How can I do that? Well, if I have a theorem like this, and I can determine this amalgam up at isomorphism, then I've determined the fusion system up to isomorphism. Okay? So that's one reason why some theorem like this would be useful. And there's some obvious analog for groups that I won't bother to write down. All right, so let's now look at two theorems on fusion systems that lead to old theorems on groups. So we had this notion of an S4 free group. Here's the right analog for fusion systems. A two fusion system F is said to be S3 free if for each subgroup P of S, the group of F automorphisms of P is S3 free. In other words, there's no section isomorphic to the symmetric group on free letters. Example, if you have an S4 free group and a CLO2 group S of G, then the fusion system is S3 free. All right, so here's a theorem. If F is S3 free, then F is constrained. So as a corollary, if you translate this back into groups, you get this thing that Glauberman essentially proved. Remember that if you have an S4 free group, then there's a non-trivial, strongly closed abelian subgroup. That's a consequence of this theorem. But this is it seems to me a much more attractive statement. Seems to me the proof's a lot easier here in the category of fusion systems, and proof involves some of the machinery that in these theorems that I talked about here, but which is non-trivial, but in the special case of these S3 systems, the machinery becomes perhaps not trivial, but very easy. So if you wanted to actually write out a self-contained proof of this, you could do so without using all this machinery, and it would be pretty short, pretty nice here. So I think this is the right way to approach S4 free groups, to instead look at these S3 free fusion systems. Okay? So that's an example of a sort of classic result, old result in finite group theory that you can prove using fusion systems, and at least to my mind get a nicer proof. Let's try to look at N2 groups using fusion systems. So what's the right analog of a, I'll call it an N system rather than an N2 system? Define two fusion system F, saturated two fusion system, to be an N system if it's of characteristic 2 type, and for each subgroup P of S, the group of F automorphisms of P is solvable. By the way, you might ask, what's a solvable fusion system? And there's at least 2 answers you might be led to. One's due to Pooch, one's due to me, and the right one here is the one that's due to Pooch. And Pooch's definitions in terms of some particular series for canonical series for a fusion system, which kind of corresponds to a derived series. My definition would be in terms of composition factors, and they lead to 2 rather different classes of fusion systems. But this is the one that would come up in Pooch's definition. Example, if you have an N2 group, then its fusion system is an N system, but the converse is false, as we'll see. All right, so suppose you have one of these N systems. Then again, all N systems come from groups. There exists a finite group G, CeLO2 group S of G, such that F is the standard example of G, and G is one of these groups here. Again, you don't have to necessarily look at this list too closely, but one thing you might look at is down here near the bottom, where you see the group M12 and its group of automorphisms. And if you know anything about the 2 local structure of N2, you know it's not a N2 group, because there's a non-2 central involution S, whose centralizer is the direct product of a group of order 2 with a symmetric group of degree 5. So of course this isn't a solvable group here, so it's not an N2 group. But the fusion system of this group is solvable, so it is a N system here. And then of course you get corresponding corollary for groups due to Thompson, Yanko, Smith, Gorenstein, Lyons. If you have an N group, doesn't have to be simple N group, then looks like one of these guys. So here you see that, of course, that the Matthew group, M12, and its automorphism group doesn't appear, but most of the other groups do appear. Here's these groups of Lie type of Lie rank 1, which appear here, and they don't seem to appear here. That's because the fusion systems for these guys are, remember, too closed. So you don't really see these coming in. So part of this theorem is easy to derive from this theorem about fusion systems, and part isn't. And remember this, there was this dichotomy for N groups, for N2 groups even, either the guys of 2 rank 2 or it's a characteristic 2 type. And if it's of characteristic 2 type and of 2 rank greater than 2, then pretty easy to see what the groups are given that you know what the fusion systems are. That's fairly easy. But for in the case where the group S is of 2 rank 2, so that'll be all these guys down here, essentially these guys here, you're getting very little information from this fusion theorem. So what's the ingredients that go into making a translation from this theorem to this theorem? Well, you need the odd order paper, the Veit-Thompson theorem. You need Goldschmidt's fusion theorem that we've talked about. You need the Signalizer-Functor theorem. You need the classification of groups with dihedral CeLO2 groups, so that's some big chunk of mathematics. You need to know what the N2 groups with semi-dihedral CeLO groups and Reith CeLO2 groups of small orders look like. So you still need a lot of very big group theoretic results, but you need them in a certain place, a place where somehow what I think of as normal local group theory somehow doesn't really come into play in a strong way. So anyway, that's what I wanted to say. Thank you.
much for the lecture. Are there any questions or comments? No?
Is there a hope of classifying the exotic systems under suitable hypotheses?
At the prime 2, yeah. There's one infinite family that's known. If I was going to guess, I'd guess that's the only infinite family, but who knows?
Any other questions?
How is it working with the, you mentioned Ron and Steve, and I've seen some things on the web now that you people are doing. Is this, I mean, is there some deadline for, I mean, what you have?
It better not be.
No, I mean, no, I just wondered if you have some.
I think they've written a draft of almost everything.
Right.
And so now, I'm not sure Richard Lyons has looked at it, but at least now I'm looking at it and giving them my comments.
And Richard's in the game now too? Or?
Yeah, but he's chairman of the department at Rutgers, and I'm not sure
Right,
he
for a
has all
while,
that much
yeah,
time.
right.
But yeah, so whatever that project, I would think will be finished in some number of months.
Any other comments? Well, let's thank the speaker again.